So this is joint work with my former graduate student, Jackson Gorham. And what I thought I would do today is present some tools that we've been developing for measuring how well a given sample approximates a given target distribution. So the motivation for this whole project is coming from large-scale posterior inference. In particular, this question of how do we scale Markov chain Monte Carlo algorithms to massive data sets. So the benefit of Markov chain Monte Carlo, or MCMC, is typically that you can approximate intractable posterior expectations, like these potentially high-dimensional integrals in red here, with asymptotically exact sample sequences, so just sample averages, like these in blue. And one drawback of MCMC is that typically every new sample point, these xi's that you need to draw, require that you iterate through your entire data set. So this can be very expensive if your data set is large. Okay, so what can we do about this? Well, this template solution has been emerging over the past, half decade. And the idea is you can approximate MCMC with what I'll call subset posteriors. So you take a typical Markov chain and you modify it so that on every step you only look at a subset of the data. And the benefit is that now you can sample more quickly, so it reduces the variance of your Monte Carlo estimate, so that's great. But the drawback is that you're now introducing this asymptotic bias. Even if you run this chain forever, it may never converge to your target distribution. So the hope is that overall, for a fixed amount of sampling time, which is all you have in practice, that the reduction in variance will actually outweigh the bias that's introduced. Okay, so I think this is very promising, but it introduces a lot of new challenges. So in particular, how do we actually compare and evaluate the samples that are being generated by these approximate MCMC procedures? How do we select the samplers? How do we pick our favorite one? Yeah.
Sorry, is there any example I should keep in my head?
Yeah.
No?
So an example of the approximate procedure or example of
Just
a posterior inference
What
problem?
is the Markov chain?
What is the Markov chain I should think of?
Okay, yeah, I can give you some examples. So simplest example that still has this problem, it would be Bayesian logistic regression. So you have a logistic regression problem. You have a data set of covariate vectors with associated labels. You posit a model, which is that each label is generated according to a logistic Bernoulli distribution with a logistic mean. You don't know the parameters. You put a prior distribution on the parameter vector, and now you're interested in the posterior distribution of that parameter vector. So you might run something like, a good example would be stochastic gradient Lanterman dynamics. So this is kind of like what's called the metropolis adjusted Langevin algorithm, where on every step to draw, you're doing a random search through space. So your vector lives in R to the D. You start by picking a random point in R to the D, so any way. You can initialize it in any way. And to choose a next point, you take a gradient step with respect to your log density, the posterior density that you want to sample from. And then you perturb it with some Gaussian noise. And usually that would become a proposal in something like a Metropolis-Hastings correction. But Metropolis-Hastings corrections are expensive. And even just computing the gradient of your log density is expensive. And in each case, you have to run through your entire data set to just compute that thing. And so what people have been doing instead is using a stochastic gradient. So they're replacing this grad log p. You can write that on the board. So here's your prior pi of theta. Theta is the unknown parameter. Pi of theta is your prior. You have a series of data points, yi, so we have a likelihood function given the parameter vectors. This is your likelihood for each data point. And you have a posterior distribution, which I'll call p of theta, which is proportional to the prior times the product of all the data points you've observed, so I equals 1 to m of the likelihoods. And a Markov chain Monte Carlo algorithm would be start with a given point, let's call it theta 0, and on every step you propose a new candidate point, so that would be theta I plus 1, and theta I plus 1 is going to be theta I plus grad log p theta I plus some step size times some Gaussian vector, which let's call Zi. That's called this is a particular Markov chain Monte Carlo algorithm. It's called the Unadjusted Lanterman algorithm. It's expensive in particular because just computing this grad log p in this case requires touching every one of the data points in your data set. And so the way that it's often approximated is to use a stochastic estimate of this gradient, much like we do in optimization. So you just choose a random subset of your data, you rescale the gradient appropriately, and you plug that in.
Sorry, what's Z?
Z in this case is going to be a Gaussian vector. We'll say standard Gaussian, so identity covariance.
So the goal here is to sample from the posterior?
The goal is to sample from the posterior. In particular, the goal is to approximate expectations on the posterior. So you're generating this sequence of points with the hope that the sample estimates, the sample averages, will approximate actual expectations. Are there other questions about the setup?
Example,
Yeah.
the unknown parameter is in a high-dimensional space, and y is also in a high-dimensional space, and
So this is think of this as an R to the D.
okay,
Y could be anything. Yeah, I haven't specified exactly what the likelihood is, but it could really be anything. So in the logistic regression example, you could think of each yi as actually a pair of two things. Let's call them, I don't know, wi and vi, and each wi is again something in R to the d. This might be your covariate vector. This is a vector of features, and this is a binary label. This is plus or minus 1. And essentially what you're doing is finding the parameters that underlie a classification model. I should say I did have an example in here, but I was told to take out as much motivation as possible. So.
Example where this suggestion backfired.
That's okay.
The
Yeah.
examples.
No, but actually give despite that finish. So still I think we'd like a little more concrete. So you're doing the distribution to classify. I think we still want to think of it in the context of an example. So trying to classify what?
Yeah, okay, great. So
classify.
more forward space over here.
Yes.
Right, so here's a typical Bayesian logistic regression setup.
Trying to do what? So what is the actual example?
Yeah, so I'll try to detail that. So the setup is Bayesian logistic regression. So you have a data set. Here's your data. They are wi, vi pairs. Each wi is a feature vector in R to the d. Each vi is a label. It's a binary class label. We're going to posit a model for how the class labels were distributed given the feature vector. So in particular, the expectation of vi, we'll say in this case, is, or let's just say vi is Bernoulli with mean given by the logistic function of theta comma wi. So far as a standard logistic regression problem. And now you don't know the parameters, so you put a prior on the parameters. Let's just say it's distributed according to normal, 0, identity. So this is our prior on the parameters. And now I'm just interested in the posterior distribution of theta given all the data I've observed. And I want to compute, say, the posterior mean, the posterior variance, and posterior predictive probabilities, like the probability of y given a new x that walks in the door. Okay, even in this pretty simple setup, we don't know how to compute any of those expectations in closed form. And so what we usually do is try to draw sample points from this posterior distribution such that those sample points, when averaged together, will give us expectations that converge to the true expectation. So I'd like to know what is the expectation of theta transpose given the whole data set that I've seen. So given my W1, V1, up through WM, VM. I don't know how to compute that. So I'm going to approximate that with a sample average. So I'm going to run a Markov chain. Usually you'd run a Markov chain that actually is converging to the posterior distribution. So sum of I equals 1 to n, and I'll have samples of my theta vector, and I'll use that as an approximation to this expectation. And that's the typical way in which Markov chain Monte Carlo is used. And that's fine, and it's particularly fine when your data set is not that large. But most Markov chain Monte Carlo algorithms at least require iterating through your entire data set to draw every new sample point, because you're conditioning on your entire data set just to reason about this posterior distribution. And so of late, people have been exploring other algorithms that try to get away from that expensive operation. And an example of an algorithm, so this would be an example of a more standard Markov chain Monte Carlo algorithm, although this isn't exactly correct, but this is called what I've written down here, this operation of choosing the next sample point is called the unadjusted Lanterman algorithm. And if instead of using this actual gradient, I replace it with a stochastic gradient that only uses a subset of the data points on each step, that's what's called stochastic gradient Lanterman dynamics. And if you run it with a fixed step size, say, even if you run it forever, your expectations will never converge to the true expectations. There'll be this asymptotic bias that's left around that's related to the step size here.
So eta is your step size. Shouldn't have you eta in front of the gradient and then square root eta over 2 in front of the Gaussian, something like that?
Yes, sorry, yes.
Just so that
That's good, yeah. Yeah, or maybe I'll use, this is fine. Good. Great.
just for people who are used to gradient descent or stochastic gradient descent, the difference is that here the variance of the noise is of the order of the step size, which is why it's not going to converge to the...
Yeah, that's right.
That's by design.
That's by design.
That's by design.
To keep some variability.
You actually want to, in some sense, you want to sample from the whole distribution and not just go to the mode. Okay. Well, so tell me, is the setup clearer? Yeah. Good. Okay. So the stochastic gradient Lanterman dynamics, that's one example of one of these approximate MCMC algorithms. There are a variety of others that have been proposed, many of which take a standard MCMC algorithm that is designed to converge to a target distribution and just impair it in some way. In some way that makes it asymptotically biased, but much faster to run. And so now you have this whole zoo of algorithms, and there's this question, which one should I use? Which one is actually producing good inferences for me? And how do I tune the various hyperparameters that are associated? So in the case of stochastic gradient Lanterman dynamics, that hyperparameter might be the step size. In other algorithms, there's typically some trade-off parameter that trades off between the bias that's introduced and the speed of the algorithm. And so we need to set these in practice. And one question is, how do we do that? I guess a bit more generally, you might ask, how do we actually quantify this bias-variance trade-off that I've been highlighting intuitively? How do you quantify that explicitly? So there are actually standard criteria for evaluating Markov chain quality and convergence. Some examples that you may have heard of are effective sample size, trace plots, asymptotic variance diagnostics. These all can be quite useful for MCMC, but they also all assume that your Markov chain is actually converging to your target distribution. So they ignore any sort of bias that could be introduced by the chain itself. And that's the problem here in our setting. So what I want to introduce are some new quality measures that are suitable for comparing the quality of different approximate MCMC samples. Okay, so this is going to be our challenge. Develop a quality measure suitable for comparing the quality of any two samples that are designed to approximate the same target distribution. And this will be our setup. So we're going to work with continuous target distributions. I'll call the target P. It will have a density little p. For now, let's just say the support is all of R to the D, like in our logistic regression example. And P will be known up to a normalizing constant, but we typically don't know that normalizing constant. In particular, we don't know how to integrate under P for most functions of interest. So what are we going to do? We're going to approximate the target distribution P with a sample. So if you give me a series of sample points, x1 through xn, in my space, x, then these define a discrete distribution, which is just the empirical distribution over those points. So let's call that Qn. And associated with Qn is a sample average. And we're going to use that sample average to approximate expectations under P. And I should highlight at this point that I'm not actually going to make any particular assumption about where the xi's came from. So you could have generated them from a Markov chain. You could have generated them deterministically, like if you're doing a quadrature rule or via typical Monte Carlo. We're just not going to make any assumptions about that. And our goal will be to quantify how well the sample average expectations approximate expectations under P. And we have a few desiderata. So we want this procedure, this quality measure, to detect when your sample sequence actually is converging to the target distribution. And we want to detect when the sample sequence is not converging to the target distribution. Yeah.
So I guess you need to meaningfully define class of test functions. I mean, otherwise it's trivially false for any.
Yeah. So I'm coming to that.
Oh, I see. Okay.
Yeah, we need some notion of what convergence do we care about. And we'll come to that. And then we also want something that's computationally feasible, so you can actually go off and use this when you're running your approximate MCMC algorithms. Okay, so given that we care about approximating expectations, I think a natural metric for measuring the quality of a sample is an integral probability metric. So it's a metric that measures the maximum discrepancy between your sample and your target expectations over a class of test functions. And when your class of test functions is very large, convergence of this IPM, this integral probability metric, which I'll call DH, to 0, implies that your sample sequence actually is converging to your target distribution weakly. Okay, so some examples of IPMs that you may be familiar with are total variation distance. That would be using test functions that are one-bounded. Wasserstein distances, the one Wasserstein distance falls into this class if your test functions are one Lipschitz. The Dudley metric or the bounded Lipschitz metric is another example. And a number of these have a problem. So a typical problem that you'll have with standard IPMs is that you don't know how to compute them. In particular, the definition of the IPM involves integration under P, and that's exactly what I don't know how to do. And so in practice, I can't compute these Wasserstein distances or bounded Lipschitz metrics. So what can we do? Well, one idea is to only consider test functions that we know a priori are mean 0 under the target. So if we could do that, then this EP term in the IPM definition would just drop out, and we only have a measure that depends on my sample. So potentially that's tractable to work with. So that seems like a reasonable idea. You might ask, how do we actually find such a class of test functions? And even if we had that, would it actually track sample sequence convergence in the way that we want it to? And even if it did, how do we compute this quantity? It still involves a supremum over all the test functions in your class. So we're going to try to answer all of these questions using some ideas from Stein's method. So Stein's method, due to Charles Stein, is typically a method for controlling convergence and distribution. It was used to prove central limit theorems initially, and to prove rates of convergence for those central limit theorems. And you could think of it as a three-step process. And so in our context, what is Stein's method? It would mean, first I want to identify an operator, let's call that T, that generates mean zero functions under my target distribution. Okay? So T will take in input functions G. In this case, they're going to be vector-valued functions for convenience. And it's going to output a scalar-valued function, and that function is always going to be mean zero under my target. And I'll equip that operator with a domain, and I'll call that G. That's the set of functions that I'm passing through my operator. Okay, so together, this T and G are going to define what we'll call a Stein discrepancy. So this is an IPM-type metric, but that has no explicit integration under P by design. So we'll call the Stein discrepancy S of Qn, our sample measure, T, and its domain G. All right, and I'll give you some specific examples of this discrepancy in a second, but first I want to show you what we're going to do with it once we have it. So typically the second step in Stein's method, once you have your Stein discrepancy, is to lower bound it by some reference IPM that you know and trust, like a Wasserstein distance. And the goal of that is to show that if your Stein discrepancy is going to zero, then that reference IPM is also going to zero. So that means you can be sure that you're detecting non-convergence, which is our second requirement. So this typically requires some intensive analysis, but you can do that once in advance for large classes of distributions, and then you can go off and use your Stein discrepancy happily, knowing it has that property. And then the third step in Stein's method is typically to upper bound your Stein discrepancy by any means necessary. And there are a wide variety of tools for doing this. In our case, this is the least important step because we actually are computing the Stein discrepancy exactly. But it is there to show you that, at least to give you the knowledge that your discrepancy measure would converge if your sample sequence was converging to the target. And so I'll show you how to do this as well. So usually, Stein's method is used as an analytical tool to prove convergence. And here, what we'd like to do is co-opt it as a practical tool that you could use to measure the quality of samples being produced by your Markov chains. So let me give you a more specific instantiation of this pretty abstract recipe. OK, so we said step one was to identify a Stein operator, an operator that generates mean zero functions under my target. And to do this, I'm going to use this beautiful idea due to Barbour. And this idea is sometimes called the generator method. And his idea was that if I can identify a Markov process that has my target distribution as its stationary distribution, then the infinitesimal generator of that process just generates mean zero functions for me, basically for free. And I've given you the definition of the infinitesimal generator here, but we don't need the general definition for this talk. I'm only going to focus on one process and one generator, and I've written that here. So we're going to consider the overdamped Langevin diffusion associated with a target distribution P. Okay, and for a wide variety of continuous distributions, this exists and has P as its stationary distribution, and the generator of that distribution is written here. And our operator is going to be a mild modification of that generator. So I'm going to call Tp of G this quantity. This is how we're defining our operator, Tp. And the main thing you should take away is that it only depends on P through the gradient of its log density. So this is something that I can compute even if I don't know the normalizing constant of P. And for those who are familiar with Stein's method, you could view this as a multivariate generalization of what's called the density method operator in that literature. Yeah?
And is the fact that this has expectation 0 under the true distribution just a result of, like, doesn't directly follow, like, that's a score?
That's right.
And it just comes
yeah, so you can just do integration by parts, and that will tell you that you get mean zero functions out. Exactly. So that's the easiest way to check that this is always generating mean zero. So there's some constraints in the G's that you pass through, but for the reasonable G's, this will give you mean zero functions because of integration by parts. Yeah. So that's great. OK, so we have an operator. We also need a set. We'll call it a Stein set, the domain of the operator that we're going to work with. And for this, we're going to appeal to reproducing kernels and make use of them. So a reproducing kernel is it's a function from, in our case, x to x, from x cross x to r. It's symmetric in its two arguments, and it's also a positive definite function, which means that if I have n points and I form the kernel matrix of all pairwise evaluations, then that's a positive semi-definite matrix. So a common example of the reproducing kernel is the Gaussian or squared exponential kernel that I've written here. We'll be considering some other ones as well. And what we want from this kernel is the fact that it induces a function space called the reproducing kernel Hilbert space. And I've written down the definition of the space here, but I've purposely faded it out because it doesn't matter that much for the talk. And there's an associated norm. This is a Hilbert space. It has an associated norm, which I've also written for you. And we're going to define our domain, our Stein set, with respect to this kernel and its function space. And so in particular, each function g is vector valued, so it has d components. And our Stein set is going to be the set of functions such that each component belongs to a unit ball, or each component belongs to this RKHS, this reproducing kernel Hilbert space, and their norms are jointly bounded. That's basically what you should take away from this definition. There's a specific way in which it's bounded, but that doesn't matter too much for the talk. Okay, so vector valued function, each component belongs to this reproducing kernel Hilbert space, and the norms are all bounded jointly by 1. And in particular, for this class of functions, if you pass it through your operator, we're going to get mean zero functions out. And you can see that from integration by parts. Okay, so the beauty actually of picking this particular Stein set is that computing this Stein discrepancy is going to be very simple, very straightforward. And so remember that we're building up the Stein discrepancy. We've now chosen an operator, this operator induced by the Lanterman diffusion. We've chosen the set associated with a kernel function. And together we'll call that quantity a kernel Stein discrepancy, or KSD for short. And the benefit of this particular choice is that this kernel Stein discrepancy is actually computable in closed form. And in particular, the way you compute it is you take your original kernel, you apply the operator TP to it twice, to each argument, and then you evaluate that kernel at every pair of sample points, and then you essentially just add up those pairwise kernel evaluations. So that's something that it's both in closed form and it's very parallelizable. So you get this induced Stein kernel, which I've written in a compact way, but you could just view this as applying the TP operator to each argument of k. And you evaluate that Stein kernel at every pair of sample points, and then you sum together the results.
Just the norm that you chose to define the Stein set, it's related to what?
So it can be arbitrary. So it can be any norm, any vector valued norm. And in some sense, for our purposes, all these norms are equivalent in the usual way that vector value norms are equivalent. And so for the rest of the talk, I'll just focus on the L2 norm. But you could do this for any norm.
And do you have applications where there is an advantage to using?
I'm not quite sure yet. I've mostly used the L2 norm. There could be some advantages if you can. There could be some computational advantages if you pick the right norm. Really has something to do with the scaling and dimension. So if you can get away with computing this for some of the dimensions, it could be valuable. But I haven't teased that out yet. And I should say that this Stein set choice was inspired by an analogous kernel that was used in the context of designing control functionals, that is, control variates that are infinite dimensional for Monte Carlo integration. That was due to Oates, Girolami, and Chopin. And if you use the L2 norm in particular, this recovers a version of the KSD that was proposed by Chiwielkowski et al. And Liu et al. Okay, so to ease notation, we'll just plug in the L2 norm for the last couple of minutes of this talk. Okay, so there are a couple of things that we wanted to show about this quality measure. In particular, we wanted to show that it detects non-convergence and that it detects convergence, right? So first, detecting non-convergence. We want it to be the case that the Stein discrepancy is going to go to 0 only if your sample sequence is converging to your target. Okay, so here's a first result in that direction, and it's for the univariate case. And this is so this is not going to be true for an arbitrary target P, but it will be true essentially whenever your target has a fast Wasserstein coupling, fast decaying Wasserstein coupling. And in particular, a certain set of distributions that satisfies this to be concrete are targets that have Lipschitz grad log P and what you might call distant strong log concavity. I've defined that here to be explicit, but you could think of it as a function that's strongly log concave outside of a ball. So this would include Bayesian logistic regression, the example that we've been talking about, student's T regression, which is actually leads to a non-concave density, but it's concave outside of a ball, Gaussian mixtures with common covariance. So in this class, this result essentially says that if you use all of the standard kernels, Gaussian kernels, Matern kernels, inverse multi-quadrant kernels that decay polynomially, then you have the property you want. You detect non-convergence. But yeah, so the way this works explicitly under the hood is that we've upper bounded a more standard probability metric by the Stein discrepancy, and that just gives the result.
But I guess my question was, is it going to be exponential in the parameters that we define? Or there's a discrepancy in this parameter?
So there are two questions. There's how does the Stein discrepancy actually relate to the underlying metric? And that depends greatly on the kernel.
Yes.
So you can get a polynomial relationship if you use something like a Matern kernel. You'll get something like a logarithmic relationship if you use a Gaussian kernel. It depends greatly on that. And there's also the question of how it depends on the target.
Yes.
So with this sort of distant strong null concavity property, maybe it's helpful to think about Gaussian mixtures, so they all satisfy this. But the separation between the modes, is kind of like a measure of the violation of concavity locally. And the bound will depend essentially exponentially on that separation. Yeah. Which I think is what you would expect. Yeah. Okay, but this is also just for the univariate case. And also, I think I probably overstepped my time. So maybe I'll just give it one more. Oh, okay, great. Excellent. Okay, so that's the one-dimensional case, and typically when you're using Markov chain Monte Carlo, you care about more than one dimension at a time. So what can we say about the multivariate case? Well, first of all, in higher dimensions, the kernel starts to matter a whole lot more. And in particular, common kernels, like the Gaussian kernel that we talked about before, actually fails to detect non-convergence even for really simple targets like a standard Gaussian distribution. So here's the result. What it essentially says is that if your dimension is bigger than 3, or your dimension is 3 or bigger, then a Gaussian kernel, a Matern kernel, which has exponential decay, and even these inverse multi-quadrant kernels, which decay polynomially, if the decay rate is fast enough, you're going to fail to detect non-convergence for some dimension, for all dimensions large enough. So for Gaussians, it's actually all dimensions bigger than 3, or bigger than 2, sorry. And for inverse multi-quadrics, it's a more, it depends on the decay rate. And the sample sequences that violate this, that send your Stein discrepancy to 0, even though they're not converging, are actually pretty simple to construct. You can just put a bunch of points on a sphere and grow the radius of that sphere. So you can essentially just shoot points off to infinity. Your Stein discrepancy will go to 0, but this is not converging to your distribution. It's not converging to any distribution. So intuitively, the problem here is that these kernels with light tails, these kernels that are decaying very rapidly, actually ignore what's happening in their tails. And so they don't detect that you're sending a bunch of mass off to infinity. So this means that tightness is important. And a sample sequence, or a sequence of distributions is tight if you can, for every epsilon, find a compact set such that every distribution in that sequence has at least 1 minus epsilon of its mass in that compact set. And so it means that none of your mass is escaping to infinity. And tightness is the piece that's missing here. So if you use any of your favorite kernels, like Gaussian, Matern, inverse multi-quadric, they will detect non-convergence as long as your sample sequence is tight. So that's good to know. That's a reasonably good result, but ideally, your discrepancy measure would just detect that for you, so you didn't have to know ahead of time whether your sample sequence was tight. It would be nice if that was just all automatic. And so maybe the last result I'll present, which is probably the main one, is that, well, we said that these IMQ kernels, these polynomially decaying kernels, fail to detect non-convergence if they're decaying too quickly. But if your decay rate is basically just right, if your decay rate is between -1 and 0, then they do detect non-convergence, and for all sequences. So essentially, they'll tell you if your sequence is not tight, if you're shooting mass off to infinity, and they'll tell you if you're not converging in any other manner. So you could just use a kernel like this inverse multi-quadratic kernel with a decay rate between -1 and 0, and then you'll have the detection of non-convergence that we wanted. Well, actually, the complementary result is that you can also detect convergence under much weaker conditions here. This will work for just about any kernel you would think to use. And it essentially says whenever your Wasserstein distance is converging to 0 between Qn and P, your Stein discrepancy is also converging to 0. So those are the main theoretical results I wanted to share with you. I have various examples of using this for different problems, but maybe given the time, I should stop here.
Probably going to ask you to present what your most exciting example is, but before that, I want to ask, one classical problem doesn't involve posterior is sampling from a convex body in high dimensions. So that's a log concave density, but it's high dimensional, and as far as I know, it's open there to detect, when you're converging. So there are theoretical bounds for how long to run various chains, but if you actually are running a chain and want to detect, have I converged, there's no good method. So can your method throw light on this?
Potentially. So, okay, so now you're in an arbitrary convex body.
But in very high dimension.
And so how do you want to measure convergence? Like what is the notion of convergence that you care about?
Well, in the end, it's still a variation, but we'll get approximation.
Okay, so you care about total variation, but that's on average across the output of a Markov chain?
Well, we're running an actual particular Markov chain. We are looking at the sequence and we're asking, is this chain, is the sequence of points we obtained so far, approximating? So here,
you see Qn is the empirical measure.
Yes.
So you can't.
So this will never converge. Yeah, your empirical measure will never converge.
Never approximating until variation.
Yes.
Right.
So you're not going to get convergence.
But if you had something like Wasserstein distance, then you could reason about that. Yeah.
But still, for instance, this theorem, it would apply in the case that Yuval is talking about. But presumably the dependency on the dimension is exponential, no?
For this direction, there's not a bad on this particular direction. There's not a bad dependence, but I think what you want is the other direction. So this is saying that if your sequence is converging,
I want yours. Yes.
Yeah. So it could be very bad. In particular, these function classes aren't that big. So if you really cared about something like Wasserstein distance, like one Wasserstein distance versus like all Lipschitz functions, there's a mismatch in the size of these function classes. So to relate this kernel Stein discrepancy to that, you have, depending on your kernel, it could be like a logarithmic dependence or a nasty polynomial dependence that would depend on the dimension. If you use a much larger function class, then you would have much less of a dimension dependence, actually.
But then computationally, it's harder.
It's harder. But we do have some work. So some work that preceded this kernel Stein discrepancy version was on essentially like solving a linear program to obtain a quality measure, and those function classes are much larger. And there, you basically have a linear dependence between that Stein discrepancy and the Wasserstein distance. So so I'd be happy to talk about that if you're interested.
Other questions?